Hey, what's up, you guys? So, in our previous videos, we covered questions 1 through 6, and in this video, we'll proceed with question number 7. So, this one right here. Okay, so now before diving into the solution, let's begin with our routine practice of revisiting the steps. So our first step is substituting our power series representation y prime, and y double prime into our main differential equation. Now we have completed 6 problems so far, so we can say that we are familiar with the power series representation for y prime, and y double prime. Then our second step is to match the exponents or the powers of x to n. So we need to make sure that all the x's of the multiple power series that we have, they all have the power of n. And then our third step would be shifting the indices of all the power series we have. Okay, and remember the third step comes after the second step, so we will try to shift them after we transformed them so that their powers or their exponents have been transformed to n. Okay, and then like I said earlier, we will always keep the larger index. So the power series that has the largest index will stay as it is, and we will try to shift the indexes of the power series which has a smaller value. So the smaller value starting index power series, they get shifted. Okay, and then we have our fourth step, which is combining the series to one. So after we have performed our second step, that is making sure that all the powers of the power series has the power n, and also all the indices of the power series start from the same index, then now we can combine them into one. And after performing the fourth step, now we will find the coefficients, okay, and we use our recurrence relationship in order to do that. And then right after determining the coefficients, we can finally find the general solution, which will be in this form, excuse me. Okay. So these are my steps, and I shall use these steps in today's problem. I have used these steps in my previous problems, and I will use these steps in all the problems in section 4.2. So let's proceed with our problem. So for today's problem, we have y double prime minus x squared y prime plus 2y equals x. So our first step was to represent all these y's into our power series. Okay, so we have our y. We all know it's from n equal to 0 to infinity a sub n times x to the power n. And we all know that this goes inside our red box. Okay, so now we have our y prime. Again, first derivation, that means our starting index increases by 1. So it starts from 1 to infinity. Then I have a sub n times x to the power n minus 1. And this gets our green box. And then we have our y double prime. The index now starts from 2 to infinity, a sub n times n minus 1 times x to the power n minus 2. So that gets our blue box. Okay, so these are my power series. So now I'm going to plug them into our main differential equation, which is this one right here. Okay, so let's go ahead and do that. So first we have our y double prime. So I'm going to write y double prime from n equal to 2 to infinity, a sub n times n minus 1 times x to the power n minus 2. And then I have my minus, and then I have my x squared. Then I'm going to add my y prime, which is in this green box. So I have summation n equal to 1 to infinity, a sub n times x to the power n minus 1. And then I have my plus 2, and then my y, which is in my red box. So I have from n is equal to 0 to infinity, a sub n times x to the power n. Then it's a bracket, and then I have my x on my right-hand side. Okay, so as I can see that I have my x squared and I have my 2. So let's distribute them into their respective power series. So let's rewrite all of this again. So I have from n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And then I have this minus, and now I know that this gets distributed with my second power series. So let's go ahead and do that. So I have summation n equal to 1 to infinity a sub n times x to the power n plus 1. Again, remember by rules of exponents that if we have the same base, which we actually do, both of our bases has an x, that means their exponent gets add up, right? They adds up. So I have one of my power of x has a 2, the other one has n minus 1. So n minus 1 plus 2, I'm left with n plus 1. Okay, and then I have my plus. Now I have a constant on the outside, so you can multiply them. You can have them on the inside of the power series, or it can stay out as you wish. It doesn't really change the power series as much. Okay, the x powers stays the same, right? So for now, I'll just keep it on the outside, keep it as it is. Okay, then I have summation n equal to 0 to infinity a sub n times x to the power n equals 3. Sorry. Equals x. Okay. All right, so this is what it looks like when we successfully performed our step 1, which was representing all of these y's into our power series. Okay, so now let's move to second step, which was matching the exponents or powers of x. So this one, and this one to an n. Now notice that for my third power series, this x already has the power n. So that means I don't really have to do anything with the third one. So the third one stays as it is, right, for second step. So it doesn't really get transformed. Okay, so the only one that gets transformed are my first power series and my second power series, only because they have different power other than n. Okay, so let's first transform my first power series. Okay, so I have n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And I know it gets transformed to, let me use my dark blue. Okay. To x to the power n. So if you notice, the only way I can make n minus 2 to just an n by adding 2 to it. So my negative 2 and my positive 2 gets canceled. So that means all I need to do is add 2 to my n's, right? So that means my a sub n becomes n plus 2. Then my n becomes n plus 2. And my n minus 1 now becomes n plus 1. Because n minus 1 plus 2 is n plus 1. Okay, so I can see that all my n's in my power series has increased by 2, which means that my starting index now decreases by 2. So instead of starting from 2, it now starts from 0. Okay, so this is what my first power series, my transformed power series look like. So now let's go ahead and transform my second power series. So I have summation n equal to 1 to infinity a sub n times x to the power n plus 1. So now this 2 gets transformed. Let me use another color. Okay. So I have summation, and like I said, this n plus 1 now gets transformed to an n. So all I need to do is subtract 1 from my n, and then my positive 1 and my negative 1 gets canceled. So now I'm just left with n. So all I need to do is subtract 1 from all my n's. So my a sub n now gets transformed to a sub n minus 1. And then my n over here on my left now gets transformed to n minus 1. And since all my n's in my power series decreased by 1, that means my starting index now increases by 1. So now instead of starting from 1, it now starts from 2. Okay, so this is what my transform second power series look like. Okay, so let's rewrite our new power series, okay, our transformed power series. So my first new power series, my new transformed power series, then I have my minus, okay, summation, n equal to 2 into infinity, a sub n minus 1 times n minus 1 times x to the power n. Then I have my plus, then 2, summation n equal to 0 to infinity, a sub n x to the power n. Just, okay, equals x. All right, so I can see that I have successfully transformed all my power series so that all their powers, all their exponents and the powers now has an n. So if you look over here, this is an n, this is an n, this is an n. So I know that my second step has also been successful, okay? Now I'm going to move on to my third step, which basically is making sure that all these starting indexes are the same. Now, again, according to our third step, we always keep the power series with the largest index as it is, and we shift the power series with the smaller indexes. So I can see that my second power series has the largest index, starting index, which is 2. And my first one and my third one, starting index is 0. So that means these two needs to be shifted, okay? So now they also need to start from 2, okay? So before we can do that, we first need to write the terms that is being excluded from the power series, right? So we have to include n equal to 0 and n equal to 1 for both of these terms. So let's go ahead and do that. So for the first one, when n equal to 0, I have a sub 0 plus 2 times 0 plus 2 times 0 plus 1 times x to the power 0, which is basically 2a sub 2. Okay? And then for n equals to 1, it is a sub 1 plus 2 times 1 plus 2 times 1 plus 1 times x to the power 1. And if we simplify that, I have 6 a sub 3x. Okay? So this is my term. My n equal to 0 and then my n equal to term, that has to also be included in this equation, and we will write them separately. Okay? Now for the third one, I have my n equal to 0, and then again, do not forget the 2. We have the 2, right? So let's not forget the 2. And then I have my a sub 0 x to the power 0, which is just 2a sub 0. Okay? And then when I have n equal to 1, then I have 2 times a sub 1 times x to the power 1. So I have 2a sub 1x. All right, so these are my 4 terms that needs to be added, okay, in our differential equation, so we can't lose them. So let's go ahead and do that. So for the first one, I'm going to have my 2a sub 2 plus 6a sub 3x. And then now I shall add my transformed power series, which now starts from n equal to 2. Sub n plus 2 times n plus 2 times n plus 1 x to the power n. Then I have my minus. Then again, my starting index, as you can see, they don't have to have any explicit terms written over here because it already starts from 2. And then I have my plus, equal to 2a sub 0 plus 2a sub 1x, then plus 2 times summation n equal to 2. Okay, let me use a red pen for that. 2 to infinity a sub n times x to the power n equals x. Running out of space here, but it's fine. It's fine. We can work with that. Okay. So now we can see that we have successfully matched all our exponents. That is these ones, these ones, these ones to n. And also we have matched our starting indexes. Okay, so that means we have successfully performed our second step and our third step. And since all those two conditions have been fulfilled, now we can combine them into one. So let's go ahead and do that. So I'm going to write these terms together, okay? So as I can see that this one, the first term, and this one over here, they're constants because they have no x attached to it. So I'm going to write this one first because, again, according to our general solution form, our constants always come first, right? And then plus 2a sub 1x plus 6a sub 3x. And then combining all of the power series together. So n equal to 2 to infinity, x to the power n. And writing the leftover terms. So I have a sub n plus 2 times n plus 2 times n plus 1. Then minus a sub n times n minus 1 plus 2a sub n equal x. Okay, so this is what it looks like so far. Good, good. So we have done our step 1, we have done our step 2, we have done our step 3, and we have finally done our step 4, which was combining them together. Now we're going to do our step 5, which was basically solving the coefficients. So these ones right here, using our recurrence relationship. Okay, so let's copy the first constants, like the constants we have. So I know I have my 2a sub 0 plus 2a sub 2. These are my constants, okay, because they're not with as there's no x attached to it. And then we're going to look at our right and see if to find the value of those constants, but that because they should have the values of the constants, right? So if I look at my right, I can see that there is no constant, right? So all my constants will be a 0, okay? And I can see that there's just one coefficient, and that is for x, okay? So my constant is a 0. Now, if that is the case, I don't know what my a sub 0 value is and my a sub 2, right? So I don't know either of the values. Now, this is my second order differential equation, and I'm also not given any initial value. And conventionally, I will always take a sub 0 as my arbitrary numbers. There has to be two arbitrary numbers because it's a second order differential equation. And the only reason we have arbitrary because we are not given any initial value. Okay, so let me write that my a sub 0 is arbitrary. Okay, so given that, this leads me to the conclusion that my a sub 2, with a little bit of algebra here and there, it's just negative a sub 0. Okay, so we have already found the coefficient for a sub 0 and my a sub 2. Okay, now let's look at this part right here, and I can see both of them has an x attached to it. So we can write them together. So I have 2 a sub 1 x plus 6 a sub 3x. And I can see at my right, I have a single x, which is just 1x. Again, it's not necessary to write a 1. I wrote that to show you guys. So now, just canceling out all the x's, I have 2a sub 1 plus 6a sub 3 equals 1. Okay. Now, again, we don't know the individual values for a sub 1 and a sub 3. And like I said, if we are not given any initial value, then we have to take arbitrary numbers. right? And since this is my second order differential equation, that means I'll have two arbitrary numbers. So I already have my a sub 0 as one of the arbitrary numbers, and then I'll have another arbitrary number. And like I said, conventionally, we will take a sub 1 as our another arbitrary number. So I can write my a sub 1 as my arbitrary number. And given that, then I can write some algebra. 1 minus 2 a sub 1. So a sub 3 is 1 minus 2 a sub 1 divided by 6. Okay, so this is my a sub 3. Okay, so we've already found the coefficients for a sub 0, a sub 1, a sub 2, and a sub 3. Now, according to my question, I need to find 5 terms. So that means I need another coefficient. So I could say like a sub 4. Okay, so now in order to find that, we have to go back to this part of our differential equation. Let me use a different color. Let me use a pink. Okay, and I can see that this expression, this series, is only valid when my power of x is greater than or equal to 2. Okay, and if I look at my right-hand side, I can see that there's no values, there's no coefficients for x when x has the power greater than or equal to 2. Okay, so if the power of my x has 2 or greater than 2, or if it's a constant, they all are going to be 0 because of what I have on my right-hand side. All right, so let's go ahead and write that. So you can write a sub n plus 2 times n plus 2 times n plus 1 minus a sub n minus 1 times n minus 1 plus 2a sub n equals 0. Again, like I said, that the only reason why it's 0 because whenever the power of my x is 2 or greater than 2, I can see at my right that there is no coefficients for powers of 2 or greater than 2. Okay, so this is the only reason why this entire thing. So as long as its coefficient it's a constant and they have the power greater than or equal to 2, this is always going to be a 0. Okay, so now I'm going to find my recurrence relation. So I have a sub n plus 2, which is a sub n minus 1 times n minus 1 minus 2a sub n divided by n plus 2 times n plus 1. And remember, this is only valid for n equals in greater than or equal to 2, and this is our recurrence relationship. Now let's go ahead and find all the other terms using this relationship. So I have when n is equal to 2, then I have a sub 2 plus 2, which is a sub 4 equals a sub 2 minus 1 times 2 minus 1 minus 2a sub 2 divided by 2 plus 2 times 2 plus 1, which is a sub 1 minus 2a sub 2 divided by, so I have 2 plus 2, which is 4, and then 2 plus 1, which is 3. So 4 times 3 is 12. Okay, so I know that my a sub 1 is an arbitrary number. And then I have my a sub 2, which is negative a sub 0. So let's plug in this value over here. So I have a sub 0 minus 2 times negative a sub 0 divided by 12. So that gives me a sub 1 plus 2a sub 0 divided by 12. And this is my a sub 4. Okay, continuing with n equal to 3. So I have a sub 3 plus 2, which is a sub 5, equals a sub 3 minus 1 times 3 minus 1 minus 2 times a sub 3 divided by 3 plus 2 times 3 plus 1. Now, if we simplify that, then we have 2a sub 2 minus 2a sub 3. Divide by 3 plus 2, which is 5, and 3 plus 1 is 4, so 5 times 4 is a 20. Now, we already know what our a sub 2 and a sub 3 is, so know that my a sub 2 is negative a sub 0, and my a sub 3 is 1 minus 2a sub 1 divided by 6. So let's plug in these values over here. So I have 2 times negative a sub 0 minus 2 times 1 minus 2a sub 1 divided by 6. And then we have our denominator equals to 20. Okay. Then again, further simplifying it, I will have negative 2a sub 0 minus 1 by 3, because 2 and 6, they cancel out, and then we have 1 by 3, and then plus 2 by 3 a sub 1, and then divide by 20. So again, using our denominator, so our a sub 5 will be negative 1 by 10 a sub 0 minus 1 by 60, and then plus 1 by 30 a sub 1. So this is our a sub 5. Okay. All right, so let's do another one. So we have when n equals to 4, I have a sub 4 plus 2, which is a sub 6, which is basically a sub 4 minus 1 times 4 minus 1 minus 2a sub 4 divided by 4 plus 2 times 4 plus 1. So now I have 3a sub 3 minus 2a sub 4 divided by 4 plus 2, which is 6, and 4 plus 1, which is 5. So 6 times 5 is 30. Again, plugging in the values I got for a sub 3 and a sub 4. So my a sub 3 was 1 minus 2a sub 1 divided by 6. And then my a sub 4, which is this one right here. So I have a1 plus 2a sub 0 divided by 12. Okay. Now again, doing some more simplification, taking 330 to lowest terms and 215 to lowest terms, then I will be left with 1 by 60 minus 1 by 90 a sub 0 minus 7 by 180 a sub 1. And this is my a sub 6. Okay. Now that we have determined all our coefficients, as in like some of our coefficients, let's now write our final solution. So it's going to be y equals, again, a sub 0 is my arbitrary number. And then I have my a sub 1, which is also an arbitrary number. And then I had my a sub 2, which was basically negative a sub 0. And then x squared, can forget that. And then my a sub 3 was 1 minus 2a sub 1 by 6. So I'm just going to write them separately. Okay, so I have 1 by 6 minus 2 by 6 a sub 1 x to the power 3. Now I can do my lowest term for 2 by 6. So let's do that. So I have 1 by 3. Okay. And then I had my a sub 4, which was a sub 1 plus 2a sub 0 by 12. Again, I will write them separately. Okay, so I have a sub 1 divided by 12 plus 2a sub 0 divided by 12. And then x to the power 4. Again, this 2 by 12 can have a lower term. So let's go ahead and do that. So I can write that as 1 by 6. Okay. Then I have my a sub 5, which was negative 1 by 60 minus negative 1 by 10 a sub 0 plus 1 by 30 a sub 1 x to the power 5, and then plus I have my a sub 6, which is this one right here. So I have 1 by 60 minus 1 by 90 a sub 0 minus 7 by 180 a sub 1 x to the power 6, and so on. You can leave the solution as it is, but if you're like me and you prefer to simply simplify further by grouping terms with like a sub 0, a sub 1, and other constants together, you're more than welcome to do so, okay? So again, just remember this step is completely optional, and if you don't want to do it, it's completely fine. And for those who actually want to take this extra step, so this is how we're going to do it. So we have our a sub zeros, right? So I'm going to isolate all my a sub zeros and make it into like one group. So I'm going to use in red ink just to show you guys the a sub zeros that I'm dealing with. So I have a sub zeros over here, a sub zero over here. I have an a sub 0 over here, and then another one over here, and then another over here. Okay, so I'm going to now write out the ones that I have separately. So I have my a sub 0. Let's use a red ink. So I have minus x squared, and then I have my plus 1/6 x to the power 4, and then I have my minus 1 by 10 x to the power 5, and then I have my minus 1 by 90 x to the power 6, and then so on. Okay, so this is like my first group, and then now I'm going to look at for my a sub 1s. Let me use a green ink for that. So I have an a sub 1 over here. I have my a sub 1 over here, then here, and finally I have one over here. So let me use my green ink for that. So my first term is an x, and then minus 1 by 3 x to the power 3, and then plus 1 by 12 x to the power 4. And then I have my plus 1 by 30 x to the power 5, and then minus 7 by 180 x to the power 6. Okay, so these are all my A1 terms. Then I have the coefficients of x, so the ones without any a subs. So I have, let me use a blue ink for that. So I can see I have a coefficient 1 by 6. And then I have over here, and then I have over here. Okay? So the first one is 1 by 6, x to the power 3. And then I have negative 1 by 60, x to the power 5. And then I have my positive 1 by 60, x to the power 6, and then so on. Okay? So this is what it looks like if you decide on grouping them. Okay, again, this is completely optional. You're more than welcome to leave the answer as this one. Okay, both are right. Okay, the second one is just a more simplified version. Okay, which is completely optional. This is something that, you can completely ignore. Okay, all right. So this was the solution of my problem number 7. I hope you enjoyed watching this video as much as I enjoyed making it, and I will see you guys in my next video. Bye.